Here we're plotting the total Gibbs free energy divided by RT, so this dimensionless number for the water-gas shift reaction, 1 bar pressure, and at several temperatures. So we're plotting is this Gibbs free energy versus conversion, and what we're interested in showing is how small the change in Gibbs free energy is for significant changes in fractional conversion. So let's look at the terms in the plot. The term here is Gibbs free energy per mole. This is the total number of moles at equilibrium. And so the important numbers are, this is the number of moles of each species. This is the Gibbs free energy of formation. And the subscript O indicates that it's at standard conditions, 1 bar, and this superscript T indicates that temperature T. Of course, R is the gas constant, T is absolute temperature. This is for gas phase. Moreover, it's for ideal gas. And so this is mole fraction, and then P is pressure. So let me label some of the others just to make everything clear. So remember, this is a summation over all of the species, I. At equilibrium, we determine the equilibrium number of moles by minimizing the left side of this equation. Let's look at what this looks like for various fractional conversions, and of course at the minimum is where our equilibrium conversion would be. So you'll note that in order to expand to make it easy to see, I've only calculated a fraction of the y-axis range. I didn't go all the way to very low or very high conversions. This would correspond to equilibrium, but notice between equilibrium and conversion significantly away from equilibrium, 60% of the total conversion range. The change in this Gibbs free energy divided by RT is significantly less than 1%, less than 0.5% in most cases. And so that's true for all of these plots. Again, equilibrium would be here at this temperature and here at this temperature. And so we can use, and we show this in other screencasts, we can use Solver to identify this equilibrium point. If we only have essentially one reaction that can occur, we could make a plot to understand how sensitive it is to conversion. And we have multiple reactions. Of course, this plot's not going to be very useful. Well, let's look at the spreadsheet briefly that was used to generate these plots. So these values were calculated using heat capacities that are a function of temperature. So here are the parameters used in the heat capacity, A, B, C, and D. Here are the parameters for the elements, oxygen, carbon, and hydrogen, of course, were used in this calculation. Obtain the heat of formation at 298 from tables. And we likewise, and let's move to the right here to see a little better, we can obtain the Gibbs free energy of formation at 298 also from tables. And then we've calculated using the heat capacity, and again these calculations explained in detail in other screencasts. We calculate the heat of reaction at temperature, Gibbs free energy change at temperature. And then to generate the plots, we use the feature in Excel that allows us to create a data table where here's the fractional conversion range, and then we generated these temperatures, and then we plotted these values of the Gibbs free energy change. That's what's in the table as a function of fractional conversion. And this spreadsheet's located on the LearnChemE site if you want to look at that in more detail.